Hi, welcome to my class in differential equation. If you have taken differential calculus and integral calculus before, then you will benefit a lot from this course in differential equation. For the many applications of differential equation, it is worth studying differential equation. Differential equation is being applied in different fields, including applied mathematics, physics, biology, chemistry, and engineering. In physics and chemistry, many of the fundamental laws were formulated using differential equations. In biology and chemistry, differential equation is used to model the behavior of complex systems. If you are familiar with the theory of conduction of heat that was developed by Joseph Fourier, the law of conduction of heat is governed by second-order partial differential equation, and it is known as the heat equation. Other applications of differential equations include exponential growth, population growth of species, spring vibrations in simple harmonic motion, predicting the return from investment over a period of time. What is differential equation? Differential equation is an equation that contains a function of one or more variables and its derivatives. Simply put, a differential equation contains derivatives, either ordinary derivatives or partial derivatives. So first we differentiate between ordinary differential equation and partial differential equation. When is a differential equation ordinary? Or when do we have an ordinary differential equation? We now consider some examples of ordinary differential equation. Consider number 1. In number 1, we are given y equals f of x. From this notation, we know y is the dependent variable. And the variable y is a function of the independent variable x. There is no other independent variable x. Y is a function of a single independent variable x. And we differentiate this equation, the derivative of y with respect to x, we denote by dy dx. dy dx represents the derivative of y with respect to x. This is actually the first derivative of y with respect to x, equals the derivative of the function f of x. The derivative of f of x we write as f prime of x. F prime of x denotes the derivative of f with respect to x. This equation is an example of differential equation because it contains the derivative of y with respect to x. And this is actually the first derivative of y with respect to x. Thus, this equation is an example of differential equation. Now, consider number 2. In number 2, we are given xy plus 3y squared equals x. In this equation, y is taken as a function of x. In example 1, the function y is defined explicitly as a function of x, except that we do not know what expression is represented by f of x. In example number 2, y is said to be defined explicitly, is not defined explicitly as a function of x. So when we get the derivative of equation 2, we apply the product rule for the first term and implicit differentiation. And we also apply what is known in differential calculus as the chain rule. To get the derivative of the first term, the product xy, we apply the product rule and implicit differentiation and chain rule. The derivative of xy equals, before we get the derivative of xy, the thing that you should remember when you get the derivative of y or a function of y, you multiply it by y prime, by chain rule, because y is a function of x. Again, by product rule and implicit differentiation and chain rule, the derivative of the product xy equals x times derivative of y, 1, and we multiply 1 by y prime because y is a function of x, and we get xy prime. But that's only the first term of the derivative of the product xy. The second term is plus y times derivative of x with respect to x, and derivative of x is 1. So the second term in the derivative of the product xy is y times the derivative of x1 or y, and we get plus y. xy prime plus y is the derivative of the product xy. Plus, we get the derivative of 3y squared. Differentiate this with respect to y and multiply the derivative of this by y prime because y is a function of x, and that's by chain rule. Whenever you get the derivative of a function of y, multiply it by y prime because y is a function of x, and that's what is known as the chain rule. Derivative now of 3y squared is 2 multiplied by 3, 6 times y, or 6y times derivative of y, y prime, because y is a function of x. Again, derivative of 3y squared is 3 multiplied by 2, 6 times y to the power 1. 2 minus 1, 1. 6y multiplied by y prime because y is a function of x. So the derivative of 3y squared is 6y y prime equals the derivative of x. And the derivative of x with respect to x is 1. This equation is another example of differential equation, and because it contains the derivative of y. In the first term we have y prime, in the last term we have y prime. Hence this equation is an example of differential equation. In particular, this differential equation is also an ordinary differential equation. This equation and this equation are ordinary differential equations. To answer the question earlier, when do we have an ordinary differential equation? In number 1, y is a function of a single independent variable. Y is a function of only one independent variable. Similarly, in equation 2, y is a function of a single variable, x. So in both equations 1 and 2, we only have one independent variable x and only one dependent variable y. The dependent variable y is a function of only one independent variable y. Therefore, we have ordinary differential equations if the differential equation contains the derivative of the dependent variable y with respect to a single, only one independent variable. Again, we have an ordinary differential equation if the differential equation contains the derivatives of the dependent variable y with respect to a single, only one independent variable x. And these derivatives of the dependent variable with respect to the independent variable are called ordinary derivatives. Let's take two more examples of ordinary differential equations. In the first example, we have 3x squared y prime minus 2x y double prime plus y triple prime equals 0. Of course, y triple prime denotes the third derivative of y with respect to x. And y double prime denotes the second derivative of y with respect to x. And y prime denotes the first derivative of y with respect to x. In this equation, the function y is a function of only one independent variable x. And these derivatives of y prime, the first derivative, y double prime, the second derivative of y with respect to x, and y triple prime, the third derivative of y with respect to x, are known as ordinary derivatives. So this differential equation is an example of ordinary differential equation. The differential equation in number 2 is also an ordinary differential equation, except that different notations are used to denote the derivatives of y with respect to x. We have dy dx to the power 2. The first derivative of y with respect to x is raised to the second power, minus 7xy dy dx. The first derivative of y with respect to x equals the root of 1 minus the second derivative of y with respect to x. This differential equation is an ordinary differential equation because the dependent variable y is a function of only one independent variable x. And this differential equation contains ordinary derivatives of the dependent variable y with respect to x. Thus, this differential equation is another example of ordinary differential equation. Now, when do we have a partial differential equation? Or when is a differential equation a partial differential equation? Consider the following function. Our function z is a function of two variables. In this given function, we have two independent variables, x and y. And z is a function of these two variables, x and y. When you get the derivative of z with respect to x, that derivative is known as the partial derivative of c with respect to x. And when you get the partial derivative of c with respect to x, you consider the other independent variable as a constant. And you differentiate x with respect to x. When you get the derivative of c with respect to the independent variable y, that derivative is also known as partial derivative of c with respect to y. And when you get the partial derivative of c with respect to y, you now consider x as a constant. First, we get the partial derivative of c with respect to x. This is the notation for partial derivative, as opposed to the notation for ordinary derivative where we use d. So when we get the partial derivative of c with respect to x from this equation, we consider y squared as a constant and y to the 4 as a constant. So 5y squared is a constant, and we differentiate this with respect to x. And we get 5y squared. The derivative of the first term with respect to x, considering y squared as a constant, is 5y squared. Plus the derivative of 4y cubed times y to the power 4. We get the derivative of this with respect to x, and we consider y raised to 4 as a constant, or 4 times y raised to 4 is a constant, and we differentiate x cubed. And we get 3 times 4 y to the 4, or 12 y to the 4 multiplied by x to the power 3 minus 1, or x squared. The derivative of the second term for x cubed y to the 4 with respect to x, considering y to the 4 as a constant, is 12x squared y to the 4. 5y squared plus 12x squared y to the 4 is known as the partial derivative of c with respect to x. We now get the partial derivative of c with respect to y. And to get the partial derivative of c with respect to y, we consider x as a constant. So 5x is a constant. For the second term, if we get the derivative of this with respect to y, we consider x cubed as a constant, multiplied by a constant 4. So 4x cubed is a constant. We get the derivative of 5xy squared with respect to y, and we get 10x y. The derivative of 5xy squared with respect to y is 10xy, plus the derivative of 4x cubed y raised to 4 with respect to y, considering x for x cubed as a constant. The derivative of the second term is 16x cubed y to the power 3, or y cubed. 10xy plus 16x cubed y cubed is the partial derivative of c with respect to y. If a differential equation contains partial derivatives like this of the dependent variable c with respect to one or more independent variables, then that differential equation is known as partial differential equation. Hence, a partial differential equation is a differential equation that contains partial derivatives of the dependent variable with respect to one or more independent variables. In ordinary differential equation, the equation contains ordinary derivatives. That means the equation contains the derivatives of the dependent variable with respect to only one independent variable. While in partial differential equation, the equation contains the partial derivatives of the dependent variable with respect to one or to more than one independent variable. That is, in partial differential equation, the function in the partial differential equation is a function of more than one independent variable. While in the ordinary differential equation, the function is a function of only one independent variable. Hence, the ordinary differential equation contains ordinary derivatives. We take two more examples of partial differential equations. Number one, we have y squared times partial derivative of f with respect to x plus 3x times the second partial derivative of f with respect to y minus 2x squared y times the partial derivative of f with respect to c raised to the power 3 equals x, y, z. In this differential equation, you can see that the function f is a function of three independent variables, x, y, and z. And this differential equation is known as partial differential equation because it contains the partial derivatives of f with respect to x. We have the second partial derivative of f with respect to y, and the partial derivative of f with respect to c. Now consider this second differential equation. We have partial derivative of h, function h with respect to m, plus the second partial derivative of h with respect to n raised to the power 3 equals m n squared times the partial derivative of h with respect to m. This differential equation is a partial differential equation because you can see it contains partial derivatives of h with respect to m and with respect to n. So you can see from this differential equation that the function h is a function of two independent variables. Those are m and n. And this equation contains the partial derivatives of these two independent variables. So this differential equation is known as partial differential equation. Again, a differential equation is an equation that contains the derivatives of the dependent variable, and the derivatives may either be ordinary or partial derivatives. Ordinary differential equation is a differential equation that contains the derivatives of a function of a dependent variable, a function of a single independent variable. Or ordinary differential equation contains ordinary derivatives. On the other hand, partial differential equation contains partial derivatives of a function of a dependent variable, a function of two or more independent variables. For our lesson 2, we will differentiate linear differential equation from non-linear differential equation. And that is all for our lesson today on ordinary and partial differential equations. If you have any questions, you write your questions in the comments below. And don't forget to subscribe or ask your friends to subscribe to my YouTube channel, Art Calison. And I'll see you next time for our lesson 2 in differential equations. Thank you.